Thank you very much for coming. As mentioned, my name is Warski. I work at Software, and we have the slides. Awesome. So yeah, once again, welcome. So I would like to talk about the various approaches you can take when you have to deal with concurrency problems on the JVM. It's a very broad subject, and I think we will only be able to scratch the surface. Maybe pique your interest in one of the directions that I will mention. So we have got a lot of material to cover, so let's start. So what's the actual problem that we want to tackle here, right? We all probably know, either because we have heard or we have experienced it firsthand, that concurrency is hard, right? And we would like to have libraries which actually help us solve these problems that we have with concurrency in our code. Here in this talk, we will only focus on local concurrency, so situations where you want to leverage the many cores you have in your machine or on your server. The other type, of course, is distributed concurrency, when you want to spread your computation across a cluster. So that's out of bounds here. So we are only looking at local concurrency at this talk. Now, Scala is often chosen because it has a very rich concurrency offering, right? One of Scala's niches is modeling domains where concurrency is a first-class concern. And there's a couple of good choices, so let's take a look at what these are. So the goals when we evaluate various approaches, the goals of this talk is, first of all, to show you how you can actually avoid doing manual concurrency, right? We don't want to deal with the locks. We don't want to deal with shared memory because we don't want race conditions, or we don't want deadlocks, right? So we want to look at how we can actually avoid doing concurrency as much as possible. And the second goal is to know your choices, right? It's always good to have some kind of overview of the ecosystem of the various possibilities so you can pick the best tool for the job. And we will take a look at 3 different approaches. We will take a look at how you can model local concurrency problems using an Akka system. Specifically, we'll use Pecco, which is an open source variant of Akka. We will take a look at functional effect systems, here represented by Zio, but Cat's effect and Monix are almost the same. There are some, of course, details on how they differ, but as far as the material here is covered, it's more or less the same. Now, I also would like to share some of my own experiments and some of my own explorations into how you can tackle these things when using virtual threads and Project Loom, which is the basis of Project Ox. And there's a couple of ways, I guess, you can actually structure such a talk and structure such explorations. So the way I approach this is that we will take a look at a simple use case of an HTTP server, which is quite naturally concurrent because you can serve multiple requests concurrently, but you can also do some interesting things as part of serving a single request. So we will take a look at a single at how you can handle a request, and there will be a specific flow of logic, and we will use the occasion to when we explore how a request is handled. So we will use that to actually see how these libraries help us to deal with concurrency problems. And we will gloss over many details, like we will often gloss over error handling and so on. So please don't be too picky. But that's on purpose because we want to focus really on the concurrency tools that we have at our disposal. So the flow of the requests that we will want to model in our code is the following. So there will be an incoming HTTP request that is going to be prepare me a meal. And first of all, when we prepare a meal, we want to look up the required ingredients. So we will race to computations. Race meaning that the faster one wins, right? And we are doing that because of user experience. So we will race one computation which is looking up the ingredients in a database, and we want to retry that 3 times in case of some connection errors. And the other will be simply a cache lookup, right? So we've got some concurrency going on here, and then for each ingredient that we find that constitutes the given meal, we want to send demand over a WebSocket. So these WebSockets are global processes which span our whole application. So there's also a technical limitation here that messages to each WebSocket needs to be sent sequentially, because that's how WebSockets work, right? We cannot concurrently send two messages to the same WebSocket. So that's the flow that we want to model, right? We've got these local computations that we try to find the ingredients for our meal, and we've got this global component where we want to send demand for each ingredient so that we can actually compose the end result. Okay, so that's the setup. Let's start with Zio. So Zio introduces itself as type-safe, composable, asynchronous, and concurrent programming for Scala. So the feature that makes Zio stand out is that it's using pure functional programming. I will assume that you are more or less familiar with how functional effects systems work and how they differ from futures and so on. If you don't worry. There's a number of great tutorials out there. Maybe you can, follow up and read about it later if it interests you. So I will assume that you more or less know like how the I/O monad works. So let's take a look at the server. So we've got the server socket. The server socket has a single accept method, right? And the accept method returns a task. A task is a Zio data structure which describes the process that needs to happen in order to actually accept a client connection, right? And in our server, what we do, we assume that the server socket is bound. So what we do is we first accept a connection from the client, right? And then once we have a client socket connected, the socket over here, that's the client socket that's connected. So once we have a client socket, we want to sequence another computation, right? Since we are in a pure functional world, to sequence two computations which are side affecting, we have to use flat maps. So we've got these lazy evaluated computation descriptions, which are represented by the task data structure, and we've got sequencing using flat maps, right? So these are like the basis of how you program using in Zio. So what happens is once you assemble this huge computation description in the end, you pass it to a custom runtime, and that is the Zio runtime. So the Zio runtime actually takes care of evaluating it step by step in an asynchronous way, dealing with concurrency, threading, and so on, which we will explore a bit later as well. So now we want to actually repeat this process, right? We want to accept one client request, then another one, then another one. So what we do is we've got this computation description over here, which describes how you can accept a client connection and handle it, which we will fill in later. But then you want to do it forever, right, in a looping way. So we can now modify the computation description that we have just created using the forever combinator. And when you program in Zio and when you program with purely functional effects, you often have these combinators which allow you to modify your computation. So now let's go a bit deeper here inside. So we have some helper methods. We've got a method to read a request from the client socket. We've got a method to write the response to the socket. We've got the prepare meal, which is like the core business logic, which we will implement in a second. And now, since we have these three methods, to handle a client request, what we do is we sequence three computations together, right? We read from the socket, we prepare the meal once we have the request deserialized, and we write the response back, right? So we are using the for comprehension to sequence multiple computation. You can notice that because we are dealing with lazily evaluated computation descriptions, right? The moment we actually create this handle socket description, it's not yet evaluated. It's just a value which describes how this request handling should be done. So the definition of the computation is separated from its sequencing. Only later we actually use this handle socket to specify where this effect should happen, right? And here we use the fork combinator to actually specify and to modify the description and to tell the Zio runtime that this should be run in the background, right? We don't want the client handling process to block the server from accepting your connections, right? So we want to do it in the background. That's the first time we actually see some concurrency. So the fork is a lightweight way to actually start a process in the background. And in Zio, we've got fibers. Fibers are like lightweight threads. So you can run many, many fibers on top of a small pool of threads. And this is all managed by the Zio runtime. We also have supervision by default, one-way supervision, meaning that if the parent fiber dies because of some error, it will also interrupt and ensure that all child fibers have closed down. The other way, it doesn't work. So if the child fiber dies, it's not going to be noticed by the parent by default in any way. So that's an important thing to know. So now let's look at the prepare meal logic itself. So here we've got some helper classes. We've got the ingredient case class. We've got the meal class, which has a list of ingredients, right? We have two methods, one for finding things in a database and one for finding things in cache, the meal in cache, giving a name. Again, we gloss over any error scenarios where the meal is not found and so on. So they have some implementation, right? But according to our specification, what we want to do is we want to raise these two methods together, right? So first of all, let's go inside out. So let's look at the find in database. So first of all, we have the find in database method, right? As I said, we want to retry it 3 times. So we modify this description, saying that the Zio runtime should actually retry this computation 3 times if it fails, right? And then we've got another combinator over here, raise all, specifying that the runtime should actually raise these 2 computations, and the faster one will win. So we provide 2 computations that should be raised. So we've got these combinators which hide this. Again, this will be done concurrently, right? There will be a fiber, 2 fibers started in the background, running these 2 computations, but you don't see it. And that's great, right? Because there's concurrency, but you don't actually have to do anything with it. What's important is that computations can be interrupted. The losing computation will be safely interrupted, and the whole race will only finish once both computations has finished, the winning one and the interrupted one. The interruption points, so the moments where you can your computation can actually be stopped, are all flat maps, so all sequencing steps, plus all compatible I/O invocations. To actually, if you have like some custom I/O operation, you need to integrate it with Zio so it can be safely interrupted and the resource can be safely cleaned up. But of course, for the common situations, that's already done in the various libraries that provide Zio integrations. So we've got quite a lot of interruption points. So these computations are usually interrupted quite quickly. And this is all integrated with resource management, meaning that there is a dedicated data type for resources, and it's actually very hard to use a resource in an incorrect, in an unsafe way. You can do it, but it's not the default way you would do it in Zio or in Cas Effect. These interruptions and all these combinators, they respect they respect resource management. Finally, there's a nice feature that's available. So here we've got some time-based behavior, right? Because we want to sleep 100 milliseconds between retries, and we would maybe want to test that, right? So usually testing anything that has to do with time is very difficult because we get flaky tests, which sometimes fail, sometimes not. So in Zio, because we have a custom runtime, we can actually use a test clock, which fakes time flow, right? We can say that evaluate all effects, and then the runtime will tell us all effects have been evaluated. There's a number of effects sleeping, and now we can say push the clock forward a minute, right? So we can write tests which are very fast, but which simulate flow of time. So that way we can avoid flaky tests. Okay, final detail that we need to complete is sending out are the WebSocket processes for the ingredients. Let's assume for simplicity that we've got a static list of WebSockets to which we want to signal demand. So each WebSocket will have a queue associated with it. And what we want to do is we take the meal and we look at the ingredients of the meal, right? And now for each ingredient, we want to send demand for that ingredient in parallel, right? So once again, we are using the for each par combinator, which hides concurrency from us, right? This demand sending happens concurrently, but we don't see any of this concurrency happening. So we simply enqueue the demand for each queue. So now there needs to be a consumer from that queue, right? Here we are producing on the queue. Yeah, that's what I said. So now there needs to be a consumer for that queue. So the consumer is actually over here. So what happens is we create a queue which is also a side effecting operation because that's shared mutable state. It needs to be controlled. So what we do is we repeatedly take from the queue, which is one operation, one process description. Then we sequence sending the actual message over the WebSocket. And because there's a queue behind, we ensure that messages are sent in sequence as our technical limitation has specified. And now we use the combinators that we already know. So forever because we want to loop it, and fork we want to have it. We want for this process to happen in the background. So that's how we can actually start such a WebSocket queue. So here we've got like an alternating take a message and send over a WebSocket process, right? And that's nothing else than an actor, right? Because we have some state that is protected by our queue. So the state here is the WebSocket, which needs to be called sequentially. And we've got a queue to actually communicate with that state. So summarizing what we have seen in Zio, we've got an approach where we've got a uniform way to describe concurrently running processes as lazy values. And because these are values, we get the fewest refactoring benefits because of referential transparency. We've got a number of different combinators which allow us to specify our concurrent behavior. We get some testing support for timers and others. On the other hand, we have quite a lot of syntax overhead because we have to use monads to compose computations. We have to use custom control flow methods like loops and so on. Fibers can silently die without anybody noticing. So we've got this one-way supervision. So yeah, so that's the Zio summary. So now let's take a look at the next option, which is Pecco. Pecco introduces itself as an open source framework for building applications that are concurrent, distributed, resilient, and elastic. So it's not that different from Zio, right? This description looks quite familiar. Pecco is an open source fork of Akka, so anything that applies to Pecco also applies to Akka. What's worth noticing is that Akka is really a huge ecosystem of libraries and of functionalities that spans well beyond local concurrency, which we are talking about here, right? Akka is often used for distributed concurrency. Here we are only focusing on the local aspect. So let's implement the same thing using Pecco. So here we will be working with futures, not lazily evaluated process descriptions. We are working with eagerly evaluated futures. So this skeleton seems superficially similar because futures and Zio and task might seem similar, but it's very only on the surface, right? In the mechanics and how it works, it's really different. We have to use flat maps for sequencing in the same way. We have a smaller number of combinators, so we cannot use forever. Instead, we have to use manual recursion to implement the never-ending loop. There's also a custom runtime. By the way, so far this is pure Scala. We haven't yet touched Pecco, right? So these are only futures. So there's kind of a custom runtime because anytime you create a future, you really submit a task to an executor, and the executor picks up these tasks and executes them one by one. So there is a custom runtime, but it's significantly simpler than in case of Zio. And yeah, and we've got this forever loop through recursion. So that's the same. That's more or less the same, right? Not that different. Okay, so let's again look a bit deeper. We've got the same three helper methods. Once again, because we are working with future, we need to use the for comprehension to actually sequence these three request handling steps one after another. So we've got the read, the process, and the write response. So, you know, once again, we are only using Scala futures, right? So far, no sight of Pecco. And you might wonder, maybe we should use an actor, really? And there's also an option, but using an actor for sequential operations might be quite a pain. So I opted to use a future, but of course you might have a different point of view. One important difference is that here computations start when they are defined. So we don't have this separation of when we define computations and then when we sequence them, like we had with Zio. So these are like eagerly started computations. And notice that here we are creating a future, and we want it to run concurrently with the server accepting process, right? So we want to be ready to accept the next time connection. So we just create the future and we just let it run. We are using a map over here, right? So we are kind of discarding the future and letting it run in the background. There should be some error handling, of course, which we don't have here. But to do some background processing, you just create the future. That's about it, right? We don't need the forks. There's no supervision in the futures. There is supervision in actors. So there's also an important thing to remember, that you need to actually handle all the errors in the futures. Okay, now let's dive into the prepare meal logic. Again, same signatures, but with futures instead of Zios or tasks. Once again, we want to retry this call to finding things in the database. There is a Pecco provided retry, so we just use that. It returns us a future which can be retried 3 times. What's important is that here we have to provide a lazily evaluated value, right? We have to write a function which returns a future so that we can actually start the computations 3 times. Now for the race success, which is over here, for the racing, we actually need to implement our own because there's nothing in the library. So we will see how you can implement this in a second. Now we want these two to happen in parallel. So we just start these futures, like we let them run. They are eagerly evaluated. What's important is that these computations can't be interrupted, right? So even if the faster one wins, the other one will run into completion anyway. There's no way we can stop the other one. And we have to use completion callbacks to do error handling. Now let's see how we can actually implement race success, and that's where we will use an actor. Now it's quite a long code. I don't want you to comprehend it. I just want you to see that it's a non-trivial amount of code. So the approach we take to actually implement a race success is we create a short-lived actor collecting responses from the futures. The implementation is quite straightforward. So the API for defining actors, here I'm using the typed variant of actors. It's very straightforward. It's very easy to understand. So it's very intuitive to understand how because you define an actor behavior, which in response to a message can modify its behavior, and you return this modified behavior, and you do it in a loop. So the mental model is very simple. And it's intuitive, but you end up with quite verbose implementations in the end. So yeah, so there are no combinations available out of the box, so we have to resort to doing sometimes things by hand. There's no interruption, as I mentioned. So now let's jump into actually the last component, which is sending out the demands to the WebSockets. So here, of course, we are in Pecco's natural ground, where we want to where each WebSocket handling process is represented as an actor, just as before, right? So we just need to send out messages to those actors. So what we do is we take the ingredients of the meal, and for each ingredient, we look up the actor that's handling this WebSocket by name, and we simply send a message, right? So this message will be processed asynchronously. We don't really need to do it in parallel. It's just sending messages is a fast operation, so that's good enough. One thing here to notice is that when we've been implementing, for example, this race, we've been using the typed API. Here, we are using the untyped API, right? We are just looking up an actor by name, and we don't know what type of messages this actor can handle. So it's kind of the typed API is a later addition to the untyped API, and I think it's a really great achievement that it's done so nicely, but there are some friction points when it comes to integrating these two worlds. So here we've got the untyped variant. So now let's look at how you can, that I mentioned, that sending multiple messages is really processing is effectively processing the things in the parallel. So let's look at how you can implement the actor. So again, the implementation is quite long, so let's not inspect it in detail, but just a high-level overview. So we've got a recursive implementation which returns modified behaviors. If you just notice at the beginning, we describe the behavior of an actor as an immutable value by doing behaviors.receive. And if you want to write a typed actor, you just take the behaviors class and you inspect, you press the dot and you see what autocomplete gives you. It's usually quite intuitive into seeing what needs to be done. So the API is really nice, but it's quite verbose. Now, integrating with futures is a bit tricky. So here, the problem is that the WebSocket.sendText, this will return a future. And only when this future completes, we should be able to send the next message, right? Because we have to send messages to the WebSocket sequentially. So we have to manually make sure, and additionally, like the whole problem is that the actor will always needs to be ready to process messages, right? So when we are actually in the process of sending one WebSocket message, we need to buffer the incoming demand messages, and only when we are done, we can send the next one. So here, most of the code is dealing with actually buffering the incoming messages so that we keep the sequential nature of the WebSocket interaction. So this future integration, again, there's some friction. So summarizing, in Pecco or in Akka, we have a single concurrency recipe, you might say, right? We've got the actors, which have a very clear mental model, and they are easy to understand. I think they are quite easy to learn as well. We've got the great API for define actor behaviors. We've got automatic supervision in actors. On the other hand, there are some mismatches in. For example, you've got these lazy evaluated behaviors, but you've got these eagerly evaluated futures, right? So you need to somehow mix and match those. Resource management is also partial, only in actors. So if you end up using futures, you are more or less on your own. Again, we get the syntax overhead, the same we had with functional effect systems. Stack traces aren't really usable, and there's no interruption, which might be a problem. So finally, let's look at what we might do, how modeling such a task might look if we have Project Loom at our disposal. Project Loom kind of bakes in an asynchronous runtime inside the JVM. So before Zio, and to some degree Akka as well, of course, they implement asynchronous runtimes as a library, and now we have it in the JVM thanks to Project Loom. So the goal of Project Ox is to explore if you can build a concurrency library which actually in some way replaces these solutions that we have talked before, and somehow emulates their behavior. So it's a totally experimental stage. It's not production ready, but some things already work. So let's start with the server. So we, in the Project Loom and in Ox as well, we are dealing with blocking code. So blocking code is fine once again. We will be doing synchronous calls. So we don't, in our server socket, we don't have any wrapper for the accept method, right? We can simply call accept in a blocking way, and that's fine, because we will only block the virtual thread. And same as fibers, a number of virtual threads are scheduled by the JVM to run on a small pool of platform threads, right? So this is done behind the scenes. We don't get this syntactical overhead here. We can just use blocking calls. So that's what Project Loom gives us. What Ox gives us are these combinators like scoped and forever. So forever, of course, that's borrowed from the functional effect systems, it will just evaluate the given code block forever, right? Yeah, we've got the direct style with eager evaluation. So now the scoped. The scoped is a very important concept in OX, and it's also championed by Java. It's called structured concurrency, and this means that any threads that are created within the scoped block are guaranteed to have finished either by interruption or naturally when the scoped block exists, right? So once control steps over scoped, it's guaranteed that there are no threads that are left behind. So the syntactical structure of your code determines how long these threads live. And the goal, of course, is to make concurrency easier to understand. So that's what scoped does. Now forever takes a computation by name. So once again, we need, we need to make these computations lazy somehow, right? So that we can repeat them. So here we are using Scala's by name parameters, which actually allow us to pass a code block in a nice way. So now let's move to actually how we can implement the meal handling. So we've got the same set of methods, no wrappers over here. We can just do blocking calls, right? If you want to sequence 3 computations, we just write them one by one. So we don't use slat maps. We use semicolons, which are not visible in Scala, for sequencing. And in a similar way as we did in Zio, we can fork a computation. So this will start a virtual thread which will do computations in the background. Supervision is optional. So it is possible to tell OX that if a child fiber dies, you should also interrupt the parent fiber so that everything winds down, right? Here we don't want that. We don't really want, if a processing of a request fails, we don't want the whole server to shut down, right? So here we don't want supervision, but you can do it. Yeah, and we've got the asynchronous runtime that's built into the JVM. I already mentioned that. So okay, let's dive into the prepare meal. Same stuff as well as before. And similar as before, we've got some combinators over here. So we've got the retry combinator, which takes this parameter by name. It's not visible, which is kind of a disadvantage because you don't really see which parameters are lazily evaluated, which are eagerly evaluated. But this will be lazily evaluated because it's taken by name. Similarly, this race success, it will start 2 fibers. It will race these computations, and the faster one will win. Yeah, so these are the race success and retry methods. Now, interruption is present in Loom, but it's using Java's interruption, which might be problematic, and I will explain in a second why. Now, interruption points in Zio or in Cats Effect, interruption points are all flat maps, so all sequencing operations as well as I/O operations. So here only I/O operations are interruption points, so there's fewer of them. Now, resource management, not visible here, but also a very important aspect. You can do resource management, of course, using try finally. However, in Zio or in Cats Effect, you had this dedicated data type for resource management. So it was very hard to misuse a resource. In Java, you can allocate a resource, and the compiler won't stop you from doing that, right? So you have the tools, but it requires discipline. So now let's look at why interruption is problematic. So let's imagine that we've got this simple background process which forever takes a message, processes a message. If there's an exception, just logs the message, redelivers it, and loops forever, right? Now, if the parent process, if the parent thread decides that it's time to finish, it will interrupt this fork. So an interrupted exception will be injected. Maybe, next message contains an I/O operation, so next message will actually show an interrupted exception, but it will be logged, right? Because it's an exception, it will be logged, and the loop will continue, and the fork will never finish, and the scope will never finish as well. So that's a bug. Yeah, because we've got these interruption exceptions that are injected. Instead, what you should do is you should only catch non-fatal exceptions over here. interrupted exception is not a fatal exception, and this will actually work correctly if there is an interruption outside. However, such an approach needs discipline, so you need to, catch the exceptions in the proper way. And it's also tricky when you integrate with third-party libraries, because if a third-party library catches an exception and discards it, well, what can you do? Okay, last component that we need to inspect is how to prepare a meal. So once we have obtained the meal, we look up its ingredients and we map over the ingredients to actually send demand over the WebSockets. Same as in the functional effects systems, we've got a statically available map for simplicity, which allows us to communicate with the WebSockets. So here we've got a sink. A sink is like a queue in Ox, but a bit better. So what we are doing is we are enqueuing the demand for this ingredient to each of these queues for each ingredient, and we are doing it in parallel. We are doing it in parallel because we've got the power combinator over here. So once again, concurrency is hidden from us. This will start a number of background fibers which we don't see. And against one, we need to manage the laziness manually. And how you can actually handle this demand and sending over WebSocket. So when we start a WebSocket channel like a queue, what we do is we start a background process. The background process continually will receive from the channel. If the channel is done, it will simply stop this whole fork. If there is some demand, it will send the demand over the WebSocket. This call over here is blocking, right? So while we are sending the demand over the WebSocket, we won't be receiving any new messages from the queue. So we don't need this buffering that we needed with Pecco. So again, we are alternating between receiving from the channel and sending the demand. And again, it's an actor, right? We've got a queue, we've got some mutable state that's protected by the queue. And this needs to be run within a scope because we are starting forks. So we are using this capability, this Ox capability, to actually delimit that. So summing up, what can we tell about Ox? There's no syntax overhead, right? Because we've got direct calls. We've got structured concurrency, which helps us delineate where how long these threads will actually live. We've got many combinators for specifying code that should run concurrently, like race and parallel. We've got usable stack traces. We've got optional supervision, which is very nice. On the other hand, we've got this mixed eager and lazy evaluation, right? Sometimes we simply need to pass in a code block that's lazily evaluated. In the functional approach, it was a uniform style which was always lazy. Here it's mixed. We've got the Java's exception-based interruption, which is not always nice. So far, also, we don't have any type safety for errors or I/O. So from the signature of the method, you can't really tell that this is a side effect in computation, which is really a shame. Maybe I'm hoping that the capabilities work might be useful here, so that we might use here. We also need to rely on system timers. So again, if you've got any time-based behavior, your test might end up being flaky. So to summarize what we've been talking about, this, like, you can put it in a matrix. And again, it's quite big, and I don't expect you to read it in detail. But the important point is that there is no single approach that is all green, right? So each one has some ups and downs. We've got, here we've got a high syntax overhead, but we've got, good interruptions. Here we've got low syntax overhead, but we've got Java interruptions, right? So here we've got a very mature ecosystem, especially true for Pecco and Akka, where there's a ton of libraries available which you can use. That is definitely not true for Ox, and it's maybe, in Zio it should really be a yellow sign over there. So, there are good and bad choices. There's a couple of good choices. That's I guess, my point, depending, of course, on your use case. So, to avoid concurrency, what can you do? So you've got these high-level methods such as racing and parallel, which help you to really hide concurrency behind this method invocation. Also something that's ubiquitous, when you've got some kind of a global process that you need to communicate from many different parts of your system, you will probably end up using actors, and that is the good thing to do. And you can use actors both in Pecco, but also in the other approaches as well, by using local actors, of course. In Pecco, you can also have distributed actors, a whole other thing. And an important part which we haven't really touched on is that all three libraries and all three approaches have a streaming component. So very often it's the case, especially when you want to somehow manipulate multiple input elements and you want to combine them in various ways, that these streaming libraries provide a great answer of how you can avoid concurrency. So they also often have combinators which allow you to process some elements in parallel, do some buffering, limit the parallelism, and so on and so on. So quite often, you know, in addition to these high-level combinators that we have talked about, in addition to actors, you can actually turn into to the streaming approaches that can help to avoid concurrency. So finally, I would like to do a quick shout-out to my company, Software Mill, just so that you know that we are out there. So we have recently merged with Virtus Lab into a single group. So we are still separate entities, but we operate as a single group. We are both very invested in the Scala ecosystem, and we both contribute quite a lot to the open source Scala ecosystem, Virtus especially in the tooling area. But our day job, of course, is to do consulting, is to do custom software development, not only in Scala, also many other areas out there. So if you would have, you know, any business problem that you would like to flesh out in technical terms, I guess we are a very good address to turn to. There's also a State of Scala survey that I think was mentioned yesterday, but if you haven't yet bookmarked the survey, please help us know how to direct our open source efforts. There's a couple of resources if you would like to explore more. I will put these slides on my webpage so that you can actually click the links. Otherwise, it's quite hard to do it here. So I've got a series comparing Scala Z8.io is Zio now, and Akka and Monix. So that's a bit dated in terms of libraries, but the ideas are exactly the same. So I guess that might be interesting from that perspective. I've got also an article where I try to implement Raft using Project Loom and Zio and compare these two approaches. The Zio and Cast Effect and Pecco docs are really great. So if you want to explore more of these libraries, take a look there. And with that, I would like to thank you. I think we even have 2 minutes for questions. So thank you very much